Okay, thanks everyone. Can you hear us, David?
Yep.
Yeah. Okay. Well, we're excited to have our next invited speaker, David Spivak, who's a very well-known figure in the applied category theory community, and particularly he's the chief scientist at the Dept Institute, where our project on consciousness was hosted, which was the support for this workshop. So very grateful to the Dept Institute. And yeah, please take it away, David.
Okay, thank you. Thanks for having me here. Nice to be here. Yeah, I'll be talking today about dynamic interfaces and arrangements, which is an algebraic framework for interacting systems. Okay, so why am I here? I actually think that this might be one of the fundamental questions of consciousness. I don't know much about consciousness, but except having it, of course. But just thinking about it, it feels like in order to flourish in an environment, wherever you are, you need to understand how you roll, my role in that environment, how I fit into that environment, what enabled me and persuaded me to be here, and kind of knowing those things. Why am I here? How did I get here? Kind of orients me to this situation and directs the way that I'm thinking about it. So I'll give an answer to why I'm here below, but let me first say why. Let me reframe consciousness to something nearby that is easier for me to think about. Or just think about consciousness at all. So I want to think about consciousness as extended and not isolated within individuals. And I want to think about it as like that which brings senses into coherence. So the structure of our brain brings our senses into coherence. It makes our sense of the situation and brings different senses we have into coherence. But I feel like there's a lot of consciousness in the built environment also. If you have a building that if things are kind of set up right, then it helps people work together, and that helping work together is like a consciousness that's embedded in the built environment. There's a consciousness that goes into building an organization in terms of its culture and its policies, and that it comes back and helps the community of people that live in that building or work in that building work better and have their sense of the situation cohere better. And so I think that trying to talk about consciousness as isolated within one person or an individual, I might call that awareness or something, but I think that there's if we do that, we might miss a consciousness that is not just individualized. So the reason I'm here is because I'd like a systematic account of collective sense-making. This is a reframing of consciousness that is easier for me to think about as sense-making. So how do different sense-makers form into a collective sense-maker? Neurons form brains and humans form organizations. We see it all around us, that we don't have our senses in some heap. They're interacting with each other and informing each other. And I just want math to think carefully about that collective sense-making. Toward that end, we solve big problems by working together and coordinating our activity, our sense of the situation and our activity towards it. And when my efforts and yours conflict, then we have friction and loss and nobody feels good. But when we coordinate, we stop stepping on each other's toes and we can work together and actually do things and align. People talk about alignment a lot in a lot of different situations, and it's important in all of them. And the way we do that as humans is we give accounts. We explain our activity in the terms of the collective. So we need other people. If I'm going to be accountable, I need to say things in a way you'll understand why I did that. And as the collective that we are, whether we're talking about a single brain or whether we're talking about a collection of individual people or something, when there's a collective and it grows and matures, its internal accounts become more systematic. So maybe at first, there's a baby and it seems to like different parts of its brain seem to be completely conflicting with each other, and it doesn't have any idea what's going on, but eventually it's working in a coordination, and that coordination is somehow that different parts of it are able to communicate what they're thinking to each other. And in the same way, that's what I'm trying to do with you guys here. And in general, I think it's important that we have this systematic accounting, because when there's friction, when I misinterpret your account of something, it causes a problem. And if your account of something hides key variables, like you're hiding something, then those are externalities I have to handle. Whereas if we get systematic, like the government wants us to do on our taxes, and we use accounting systems this systematicity increases the transparency and the communication rate and reliability. So we can start to regulate each other, have things be more regular. And I think that people talk a lot about predictability in, say, Kristen's work and that sort of predictive processing stuff. I wonder if regularity might be just as important. A chess game is regular, like the pawn still moves left, but it's not predictable. So regulation is just that you can't move your pawn left, and then the other person does, oh, oops. And in the same way, math is also very regulated. A mathematician wants to be corrected when they make mistakes. So I think of mathematical fields as crystallized accounting systems. They're very, very systematic. And I'm using the word accounting in two different ways, kind of like accounting like in spreadsheets, but also just giving an account of something. So arithmetic is how you account for the flow of quantities. As in finance, you can use plus and times. Whereas Hilbert spaces are the way you can account for the states of elementary particles. And probability distribution are the way you account for why someone's winning at poker, or calculus for rates of change. If you want to give an account of that, that's the language to use. It's a crystallized accounting system. And so what I would like is systematic accounting for collective sense-making. All these people, Newton and Pascal and Frege and Hilbert and all these people, saw some phenomenon in the world, and they saw it had enough consistency to it that they could find a crystallized, lawful way of talking about it, and a system that wouldn't let them down. And so we see collective sense-making all around us, so we should be able to have an account of it, a systematic account of it. We would just need to track the phenomena we're talking about and articulate the structure and systematize it. So what is that for sense-making? That's the question. Now, category theory it's all mathematical fields. If I had to commit to saying that they're all crystallized accounting systems, then I would have to tell you what category theory is the accounting system for. And it's the accounting system for interlocking structures. So mathematical definitions are composed of interlocking structures, and category theory tracks the layers of structure and their connections. So this makes it so you can have analogies, which are similarities of structure. You can make them into formal objects. So category theory is trying to account for the fact that we can make formal analogies. The fact that different accounting systems, different ways of seeing things, from arithmetic to probability to calculus, that they cohere into a larger whole. So this coherence is something category theory is good at talking about. The word coherence properties is all over the field, but it's also, I'm also noting that that's kind of what I said collective sense-making is, that we want our senses to cohere. And so I think it's a natural language. And so the goal is to use category theory to articulate the structure of collective sense-making. What are the interlocking structures that make that possible? So collective sense-making is all around us. It's in our science, it's in our technology, it's in our governance, our morality. And each of these things is the product of our work over millennia. And our body is a collective of cells whose individual intelligences work harmoniously to create the intelligence at our own level. So that's what we're aiming towards. I want a language and logic for the shape of this. I want to be able to talk about this leveling up where, if you have a bunch of little sense makers, they create a larger level sense maker. I don't know if it's conscious. So that's why I avoid the word consciousness a bit. But I do think it's making sense. And so rather than understanding like kind of the lowest level of physics and using emergence, this kind of almost magical concept of emergence to get us to human intelligence, I want to look for construction principles that are compositional the whole way up and down. So I want an algebra by which interacting sense makers form a sense maker, and that's where we're going today. Although I will not say that I can't say that I've succeeded at this. It's just that that's what I want, and that's the direction of the talk. And so the math that I'll be talking about is called dynamic organizational systems. But the idea is that any life form is a collective, a dynamic organization of smaller parts. The organization provides an interaction pattern for the parts. It says, kind of creates the spaces and possibilities for how they're going to interact. And the interaction itself changes the structure, can change the structure. So RNA interacts with the nucleus and the ribosome, And what occurs during that interaction can change the organization. It can change the proteins that are being expressed in the cell right then, which can change how the RNA is being read. So, or death is something that can happen to a person and then the organization disintegrates. Or a CEO might see what's occurring and change the org chart of the company. So just like when you started this talk today and you introduced me, and then it was my turn to talk, the stuff that's kind of flowing through the wires of our connection is changing kind of who's talking and the organizational structure itself, often like as much as death or as much as a CEO changing the org chart or whatever. So right, so I'm trying to find an accounting system for this, where you have dynamical systems that interact with each other according to some pattern, but that pattern itself can change based on what flows. What flows here can change how we're interacting. And the category theory tool that I'm proposing is called dynamic organizational systems, and it's based on a theory of something called polynomial functors. And an example is training deep neural networks is an example of a dynamic organizational system. And so is prediction markets in a simplified version of Hebbian learning. We could hope that Hebbian learning itself, a non-simplified version, could be a dynamic organizational system. But the question I'm wondering about is whether this is sufficient as a kind of framework for talking about collective sense-making. So the plan is that I'll give an account of sense-making and collective intelligence. I'll try to go into that a little bit more what I mean. Then I'll talk about polynomial functors, and it'll get a bit more technical. I'll talk about dynamic organizational systems, which are based on polynomial functors, and then I'll stop. Right, so by sense-making, there's a pun here that I'm wondering, maybe it's not a pun. So we want to understand collective sense-making, but what is sense, and what does it mean to make sense? And so by sense, I don't mean like the kind of thing that like a sensor would bring in. So the word sense is a bit overloaded. I mean more like what people call a spidey sense, right? Spider-Man has this sense of danger, say a sense of danger you could have, or a sense of opportunity, a sense of direction. You might know where the exit is right now without having to think about it almost at all. So these aren't mere perception, they're tracking the right variable. So if someone has a great sense of humor, they're tracking something about the situation that allows them to, like, with perfect timing, say the right thing at the right time, right? So what is it that sense of humor, that sense of direction, that sense of danger? When we have a good sense of something, we navigate it with ease. And that's the thing I think that I want to talk about. What is sense? And now I want to consider a snapshot. Just imagine two math students in the same classroom. And they both want to succeed. They both care about that. But the first one, I've had students who want to succeed and they copy the answers from the back of the book and they hope that while they're copying them, they're kind of taking in the idea. And other students faithfully copy down everything the teacher says. Then imagine student B, and they're doing almost the opposite. With the teacher, instead of faithfully copying down everything, the student is clearly frustrated. They're saying, wait, but no, I don't, how could, look at that 6, but you wrote 8 over there. And then the teacher says something, and then the student kind of goes, oh, and they say, is it because of, ABC? They something clears up, right? And they relax, and they feel good. They've made sense, right? And then later they do better on the test. So that's what we call, they say, oh, that makes sense. And if something doesn't make sense, we can't operate there. And when something does make sense, we can. But look at what the student actually did. They were frustrated, they were working, they were trying to figure something out, and they were working towards that. And they were, I want to say that that's not a pun, that they were making sense. Because the effort that they put in fact, created a sense of that mathematical thing that they could then navigate with ease. So I wonder whether, this work actually is where our senses have come from. Something like some abstraction of the work that the student is doing. Is that how all senses are made? Like, is there some sort of work that can be done where you try to get things into alignment and they're not fitting, and then boom, they fit together, and this kind of relaxing happens. So yeah, I'm wondering whether the work of trying to make sense of things is where new senses come from. Okay. So how are our senses made? Our sense of danger, our sense of sight? Could it be that past sense-making activity is somehow installed into deep structures that account for the senses we have today? So what I mean by that is like our sense of beauty and goodness might be how we choose our mate. So mate selection is based on our sense of good and beauty, say, and then we install that into the deep structures of our DNA. We mate and we have new children based on those senses. So we install those senses we have in our life into deep structures. Or if someone like uses a microscope for a certain kind of try to figure something out, and they notice a certain pattern in the way they use it, often that pattern is installed into the deep structure of the next microscope. So I think it's possible that this sense making is that we're installing our senses into the deeper structures. And I hypothesize that it has something to do with proper accounting. Because when I shake my head and say, no, that doesn't make sense, it's because there's something that's unsettled. There's something left over. There's something that doesn't fit. And when we jiggle the pieces and then we try different arrangements and something clicks and something settles, and that settling of accounts, we're like, all the different accounts of this are fitting together now. And now I don't have to work so hard to understand the next new thing because it fits into a settled account. Like if my checkbook is settled, then when I get a new check in there, I know exactly where it's supposed to live, what it's referring to. So then things become regular. We find this articulation that regularly captures the relevant aspects, and that's the sort of thing we can write down and we can install into deeper structures. Once we understand it, once it becomes regular and kind of part of how we're working, then it can be installed into other things. So, for example, making math is once you understand something, you might be able to make math of it. So now I've made a few claims that I want to recall here all together. First of all, I think that the question of why am I here is fundamental. I think consciousness is that which brings senses into coherence, and I think the production of higher level sense has something to do with proper accounting. So soon I'll be talking about math for dynamic organizational systems. These are different dynamical systems that interact within a sort of ecosystem. I only have a few examples so far, artificial neural networks, prediction markets, but I would love help creating a dynamic organizational system of sense makers. If artificial neural networks are optimizing the functions, what would sense makers be doing? So if sense makers want to cohere, they should understand their own fit, right? So fitness, instead of meaning how strong or fast you are, maybe it means how much you fit in the environment and provide what's needed there. And so when the sense maker, that student B, understood the math, they saw how everything fit. So this why am I here and how do I fit and what is my role? Those are the same question. They're asking how do I fit in? How do I account for myself here? And so if each member of a collective has a good sense of their own fit, then it creates a coherence because they understand what they're supposed to be doing to make the other one happy and what the other one should be doing to make them happy. And that creates this higher level order collective sense. If I have a sense of what's wrong, then I don't have to ask every time. I can just go there directly and help. So I was trained as a mathematician, not a philosopher, so I don't want to philosophize this whole hour and instead present some math. But it's intended as an accounting system for this relevant thing, the question of coherent interaction of dynamical systems. So next I'll introduce the main tool, which is polynomial functors. And despite the boring name, they're stunning objects. I'm shocked at how amazing they are. So I did not invent them. They've been around since the 70s or 80s in various forms, but they're the most highly structured and unreasonably effective abstraction I've personally ever seen. So I just fell in love with them about 3 years ago, and so I'll be talking about them, and they're the basis for dynamic organizational systems, the mathematics. I'm going to explain polynomial functors at a bunch of different levels simultaneously, so you might not understand some parts of it, and that's okay, just let that part go. I'll try not to leave you long without something you can make sense of. Just listen for the part that's supposed to be about what we're talking about here. So polynomial functors, Eugene Wigner lauded math as unreasonably effective in the natural sciences, and lots of his assertions also, if you look at them, they'd affirm the effectiveness of category theory in math. And he does mention the miracle that is our ability to make sense of the world. But I think maybe the real miracle, a big miracle, is abstraction. And abstraction is a bidirectional thing. So this is a kind of new way of thinking about abstraction that I got from polynomial functors. I was thinking, what are polynomial functors really about? And in some sense, I feel like they're about abstraction. So what is abstraction? You take a concrete situation and you boil it down to an abstract one, right? You start with that. This is very high level and not very deep, but let's just look at it like that. So you take this concrete situation, this particular leaf wiggling in this particular wind, and then you imagine it as a leaf or a thing or whatever. So you take this concrete situation C and you boil it down to an abstract situation A. But then it's bidirectional in the following sense that you don't just stop when you get to the abstraction. You take conclusions. If that abstraction gives you some problem, what am I going to do with this leaf? What am I going to do with this object? You take conclusions about objects, things you can do with objects, or things you can do with leaves, and you can transport them back to the concrete situation you started with. So it's two directions, and that's what polynomial functors are going to be about. We'll see that on the next slide. Now, I think this category of polynomial functors is unreasonably effective for computer science. In some sense, it's all about plumbing abstractions. So it's kind of weird when you first learn about it. It's a different sort of category than, it's a category. It's a very, very normal sort of category. But there's something weird about this two-directional thing. You boil something down from concrete to abstract, you take conclusions about the abstract thing, and you pull them back. That two-step process is a little bit unusual in math. Usually things kind of go one direction. But it's all based in set theory, so it's all very easy to think about. But then it's also got tons of structure. So I'm trying to think if you've ever heard of a category that had all limits and all colimits. Okay, fine. A lot of categories have that. 3 different orthogonal factorization systems. Probably haven't heard of many of those. Have you ever heard of a category that had 2 monoidal closed structures? Maybe, but maybe not infinitely many. This has infinitely many different monoidal closed structures. It has co-closures. It's the comonoids in poly. If you take the comonoids for one of the composition product structure, the comonoids are exactly categories. Every category is a comonoid. Every comonoid is a category. It's monoids, generalized operads, etc. It just keeps going. But it also has tons of applications in computer science, like Moore machines and Mealy machines, which are basically finite state automata, like dynamical systems or automata, database and data integration, algebraic data types, like in Haskell or functional programming language, bidirectional transfer. If someone's heard of lenses, those are very special polynomial functors. Bidirectional transformations, dependent type theory, effects handling, cellular automata, rewriting workflows, and deep learning, which I'll be talking about a little bit today. So it's got tons of applications in computer science, but it's also got tons of structure. So what are they? So we're starting to get into the technical stuff. A polynomial P is you can think of it like a data structure, but on the left here, you see y squared plus 3y plus 2. And now, if you plug in 1 for y, you get 1 plus 3 plus 2 is 6, and those are the 6 dots across the bottom here, and the 6 dots across the bottom here. And then above the first dot is a 2, an exponent of 2. Above the second dot, the second 3 dots is a power of 1, y to the 1. So above these 3 I have 1, and this is y to the 0. And so I have 2 dots with 0 things. I often talk about the dots on the bottom as positions, so this has 6 positions. And this position has 2 directions. Okay, so this position has 1 direction, this position has 0 directions. So polynomial functors for a mathematician, they'd be sums of representable functors from set to set. So for any set S, I'm going to write y to the power S, just like I did here, y to the 2, y to the 1, y to the 0. For the set of functions from S to whatever, some unknown future, some unknown thing you're going to tell me later. What are the set of all S's functions from S to that thing? So for anything you tell me, I'll get a set, the set of all functions like that, and that's the functor represented by S. So a polynomial is a sum, like this is the sum of 6 representable functors, y squared, y1, y to the 1, y to the 1, y to the 0, y to the 0. And the morphism of polynomial functors is just a natural transformation. But if you don't know what that is, I'll tell you on the next slide what it feels like, and why it has something to do with that abstraction picture I showed before. So this I here this indexing set is P of 1. That's what I told you to get here, the 6. And that's a convenient fact. And then I'd write like P bracket 1, P bracket 2, P bracket I for the I representing set. Okay, but so for us though, for consciousness or sense making or whatever, we want to be, for like kind of the applications, we want to think of a polynomial often as an interface. Like something is hidden behind this, but this is like the front that we're looking at. And it's got a set of types, say. Well, there are 3 different ways to think about it, so that I'll talk about today, or right now. A set I of types, and each type I has a set of terms. So this has 6 types. This type has 2 terms, this one has 1 term. Or maybe I is a set of problems. And there are 6 problems here, and this problem has 2 solutions, and this problem has 1 solution, and this problem has 0 solutions. Or for a kind of conscious entity, a sensing entity, I might be a set of body positions, like whether you're curled up in a ball with your eyes closed, or whether you're running around or whatever, that the different positions of my vocal cords as they're producing this sound. There's a set I of possible body positions, maybe 10 to the billion, I don't care. I could be huge or I could be 6, like it is here. And each position has a set of sensations it can receive. So here you're receiving 1 of 2 sensations, or maybe P bracket I is a million pixels. That's just the number of possible sensations. So like RGB to the 1 million might be what you see on the screen. Okay, so let's look at this polynomial, y cubed plus 2y. There it is, y cubed, 2 different y's, and y to the 4th plus y squared plus y to 0 plus y to 0. What is a map between them? Well, a morphism between them delegates to each p position. It says, here's my q position. Here's the abstraction of it. Now, again, this is just fully formal. It's not actually abstraction in the sense of like what we're used to. Exactly, it's a framework where what we're used to could fit. So every morphism, we take the abstractions here, or we take the concrete things here, and we boil them down to abstract things over here. So each position is into a q position, and then all the directions there are passed back. So anything you can do with that abstraction comes back and lands at one of the things you can do with the concrete thing. So P abstracts each problem in P to a problem in Q, and then implements each Q solution as a P solution. That is what a map of polynomials does. But now there's lots of operations on polynomials. So if a polynomial is an interface, P and Q, there's a lot of ways to get a new interface from them. This one, this one, this one, this one, this one. At the bottom of this slide, I actually have formulas for all of them. But so for each one, I'll say what the problems and solutions are for the resulting interface. So let's say you have 2 interfaces, and an interface is just some problems, and for each problem, a set of solutions. So what is a problem? What is a problem in the sum interface? It's a problem in P or a problem in Q. And what's the solution to it? The solution in P or the solution in Q. So that one's pretty easy. You just add them together. P times Q, this is the product in the category of polynomial functions. A problem is a pair of problems, one from P and one from Q, but you just have to solve either one. The Dirichlet product, this is another monodal product. There are infinitely many, but I'm just going to tell you about 4 today. The Dirichlet product, a problem is a pair, just like it is for a regular product, a pair from P, a problem for P and a problem for Q, but you have to solve both. The substitution product, P triangle Q, what is a problem? It's both a choice of a problem in P, and for every solution to that, a problem in Q. And that's one problem in P composed Q. And how do you solve it? You solve the problem in P, that opens up a new problem in Q, and you solve that. Now there's one more thing, the internal hom for a tensor, PQ in brackets. A problem for this is a map of polynomials, this abstraction thing. So a problem is the creation of this abstraction. So someone gives you this as a problem, this abstraction for P to Q. And to solve it, you have to give a problem in P and a solution to its image in Q. Now I'm not saying that this is like what you would think of, this is just what the math tells us. Okay, so if they're not exactly what you would think of, then maybe calling it abstractions is not exactly the right way to think about it. we have math that is very close, that seems close to this notion of abstraction, but I'll tell you what it actually does soon. So here, just for the slide, if anyone wants the slides later, all these things have formulas. The product, the tensor product, the composition product, and the internal hom. And they can be a little complicated to look at, but they're saying what I said up here. Now we'll be interested in more machines, which are open dynamical systems. And these have interfaces. And we've been talking about interfaces for a while, so these little boxes will be represented as polynomial functors. So where I'm thinking of the A and the B as sets, and kind of this, what kind of set are they? They're what can flow on this wire. So maybe this is images flowing here, and sounds are flowing here, and here is like the position of your arm, and here is like where your eye is looking, and here is what's coming out of your vocal cords right now. So the input ports I'll draw on the left, and the output ports I'll draw on the right. And by an AB dynamical system, I'll mean something that has internal states. So in this box is the interface for something. And inside of this box is this dynamical system with a set of states S. And that's like all the positions of your neurons and your cells and how each one is expressing itself right now. That's S, the total huge, gigantic, geometrically large set of states of you or me or your computer. And so for every state that's internal, there's a readout. So I can see something of it. I can see how your face looks, or I can see I can hear what you're saying, or I can see your body position. And that's something about your internal state, not what your ribosomes are doing and what your, what your muscles, not like everything internal to you is doing, but what you're expressing. That's the readout. And then you can also update, given a state and an input, you get a new state. So you're in some state, you're a little bit happy and a little bit tired, and your cells are doing this and that and the other thing, and then you eat some food, and then that changes your internal state. So that state with input gives a new state. And all this stuff that I just said is called a Moore machine, and is nicely represented in polynomials. So this interface here is represented by the polynomial b, y to the a. And this interface would be b1 times b2 times b3, y to the a1 times a2. And that's just a pattern that you can get used to. It's a polynomial associated with every one of these boxes. And the readout and update are defined by a single polynomial map. That's a natural transformation, if you like that kind of word. These are functors, and this polynomial map is a natural transformation. Or you can think of it as this abstraction thing that takes the whole state of you and abstracts it to just what you can read out, just what's on your face, just what's coming out of your voice. And take that abstraction. Now, the world solves that. The world responds to you. It says, here's what I can give you back. And it gives you an A, something coming in through your input ports. And that input, together with the original state you were in, comes back and updates the state to a new state. And so that's the Moore machine. And it's all contained in this notion of polynomial functor and morphism of polynomial functors. So, and now here's a picture of a wiring diagram, like you might find in control theory. Very simplified. You have a plant, a nuclear plant or something, and there's something happening from the outside world. And there's also, the plant is like delivering something to the outside world that we can see, but that is also being fed into a controller. And that controller then sends some information to the plant to update it and keep it in a regular state. So here the controller, as you can see, is b, y to the c. Output is b, input is c. The plant is c, y to the a times b. The y is kind of just a placeholder, but it does mean a representable functor. Like so, however you want to think about it. So we cy to the a times b, and the whole system, this whole outer box is also one. Its internal state includes these two, but it from the outside world is just seen as a system. So, and its type is c, y to the a. And this wiring diagram itself represents a map of polynomial functors. Each one of these is a polynomial functor. I tensor them together. It says if I want an output, like if I take the output of this one and the output of this one, and that's enough to get the output of the system, and give it an input to the system, and the current output to these two, that's enough to feed the controller and plant. said so far, a wiring diagram is a map of polynomial functors, but also each Moore machine is a map of polynomial functors. So what's inside the boxes and what puts the boxes together are both of the same nature, mathematically. And so we could tensor these two Moore machines together and get a new Moore machine. And then we could compose, so we could tensor these together and then compose with wiring diagram and get a Moore machine for the whole thing. So it's all polynomials through and through. All the polynomials we've been using so far are monomials, meaning they're not like ay to the b plus cy to the d. They're monomials. If you want to use something where the interfaces can change, so sometimes you're curled up in a ball and you can't feel something that you can't see through your eyes, and other times you can see through your eyes because they're open or whatever, you can allow for that mode dependence, the mode you're in, the communicative mode you're in, to change. And that would be using polynomials rather than mere monomials, but we won't talk about that today. So there's a little bit more to say about open dynamical systems. So I just said that a Moore machine is a map from sy to the s to by to the a. That's equivalent to something a lot of category theorists know, which is called coalgebras. This is actually a co-closure of S and S. You don't know what I'm talking about, but basically an AB Moore machine is equivalent to a functor from S to by to the a composed S. That's called a coalgebra. So a lot of people think about behavior in terms of coalgebras. Now there's another whole type of dynamical system called Mealy machines. So there's Moore machines, there's Mealy machines, but they're actually interconvertible. They just have different forms. So a Moore machine, as I said, is a set of states. Every state reads out to an output and can update to a state, and that's one of these. A Mealy machine takes a state and an input, and not only gives you a new state, but it immediately gives you that output. So the current output depends not just on the state, but on the state and the input. So in the Moore machine, it just depends on the current state. Now, how are they interconvertible? Right, so as I said, the Moore machine takes one step, one moment to take inputs to outputs, whereas the Mealy machine is instant. But they're interconvertible in that an AB Moore machine is just a special kind of AB Mealy machine. It's just one where the B only depends on the S, not the A. So this function can be asked, you can ask it to factor through, in categorical terms, to factor through the projection from S times A to S before it gets to B. So that's just a special Mealy machine. But an AB Mealy machine is an B to the A Moore machine. If I was, instead of outputting B here, if I was outputting functions from A to B, then it would be the same as this. So you can go between the two of them. They're interconvertible. It's just that the Mealy machines are working faster, and so that makes, if you want to turn one into a Moore machine, you have to make a huge output space, one that can take, where the output space actually contains a place for the input in it. Okay, so now we've talked about polynomial functors and dynamical systems in their terms. Let's move on to dynamic organizational systems. So what I want you to imagine is the category of sets. So all the sets in the world and all the functions. But now imagine that morphisms are dynamic. And what I mean by that is, often we think of a function as it's a black box. You put a little coin into the top and a little thing comes out the bottom, right? And then you run that function again and again, and it always does the same thing. But instead, imagine a machine that has states. And in this current state, it is a function. It's a function that takes an A and gives a B. But given that input, it not only tells you the output, but it also updates its state. And you get, I want to think of that as a more dynamic function. So you have a baseball glove, you have a computer, you have anything that you ever worked with in your life. And you think this thing has a function. If something happens to it, it'll do a certain thing. But imagine that as you use the baseball glove, or as you use your brain, or as you use the computer, it changes, the way you're using it changes the function that it is. So yeah, it'll respond to whatever you give it, so it is a function. But as you start giving it the same sorts of thing over and over again, the state of the machine, the state of the baseball glove, or the state of the brain, or whatever, morphs based on those inputs. And that's what I want to call a dynamic function. At every state, it gives you a function from A to B, but whatever you input to it changes the state. And these are exactly the AB Mealy machines. So it's a function from S times A to S times B. These fit into a more general framework, though, called where basically a Mealy machine is an AY BY coalgebra. So for any two polynomials P and Q, a PQ internal hum PQ coalgebra is a dynamical system that outputs interaction patterns. It outputs those wiring diagrams, for example, and then based on what's flowing through those wiring diagrams, it updates its state. So the CEO puts together all these different things, all these different little systems into a wiring diagram, and then listens for what's flowing on the wires. And based on what's flowing on the wires, can change the org chart. So, so Mealy machines are the case of PQ coalgebras where P is AY and Q is BY. You could just go through the definition from way back when and this internal hum thing, and you could write it out for yourself and check that it's exactly the same thing as one of these. So there will be two more technical slides. The definition of org. Org is a bicategory. Its objects are polynomials and its morphisms are PQ coalgebras. So that sounds very fancy, but it's a way of packaging up everything I've been saying so far about little machines that can wire together, and then based on what's flowing through them can change how they're wired together. So it's a machine that outputs interaction patterns. Heavy learning itself or something is a machine, is a way of working where you output interaction patterns. You output the synapses and myelination or whatever words I should be using for how the neurons are connected now. But then you listen, if you're heavy in learning itself, you listen for what's flowing through those wires, and you use that to change the wiring diagram, to change the weights, to change the quality of those synapses. So it's a function that whose input is what's flowing on the wires and whose output is what the wiring pattern is. So artificial neural networks in terms of org, let's let T, for like tangent bundle or something, T, or cotangent bundle, be a polynomial. The sum overall of this set, x in R, of y to the cotangent space at R. Okay, that sounds very fancy. It's isomorphic to ry to the R. So these could be any sets. They don't have to be 6, 6y to the 2 or something like that. These could be huge sets. And the polynomials here, the positions are points of real numbers. And the directions are the gradients. So the points are where you are, and the positions are where you are, and the directions are where you're going. P tensor T, using the Dirichlet product I wrote before, is R squared. It's just like the cotangent bundle of R squared. So it points and directions you can move. And similarly for Rn, is T tensor itself n times. What is a T tensor itself m times T tensor itself n times coalgebra? Well, it's a set of states or parameters or weights and biases, whatever you want. Okay, so all the weights and biases in an artificial neural network. That is the set S of all possible states. Not a state of each neuron, but each neuron gets a state, and the set of all possible ways of doing that is S. And then for any current state, the ways that weights and biases are right now, you get a function that takes an input and gives an output of these dimensions. And then you also get this pass-back thing where the directions go backwards. Once you've abstracted forwards, then someone gives you an answer to that. And they say, no, you're bad, you're wrong, or you're good. They give you a reward, or they give you a punishment, or they give you a gradient vector, and this is just for neural networks. In general, they give you some response. And so given the place you are now, all the weights and biases that are current, and the the input, the y prime in the current state, the current cotangent vector, I get a new state, which is the updated state from learning, and I get a cotangent vector going backwards that'll be backpropagated to my neighbors behind me. So this would be called updated backprop. It takes an input and a gradient and returns a new updated state and a backpropagated gradient vector. And this is all just, okay, so what am I saying? I'm saying there are many, many coalgebras, but gradient descent, the gradient descent backpropagation formalism found in neural networks is this dynamical system, this coalgebra. You pick a natural number of parameters. You pick a function from the parameter space times the input space to the output space that's differentiable, and you pick a parameter itself, the current weights and biases. And now that state is updated by a training pair. It keeps the parameter space and the function the same, but it updates the parameter p. And so given a training pair of an input and a gradient output for the output, like which direction you're supposed to travel, you get a new parameter. Prediction markets are also an example of a dynamic organizational system, but let's see what I mean by prediction market. So there's a fixed set of outcomes, and every participant in the prediction market produces a prediction function. They say, oh, I think it's more likely that this person will win. I think it's 50% likely that this person will win, and 25% likely that B, and 25% that C will win. And so they give some probability distribution. That's delta is a set of all possible probability distributions. And by delta plus, I mean those. The problem with prediction markets is if every single person was wrong simultaneously and had bet everything, then the whole thing kind of breaks. So let's assume that that we're not going to let that happen. So each participant receives a result. So in a prediction market, you make a prediction, and then every predictor receives a result, and that's an element of the set of outcomes, who actually won. And now to make it a market, we actually assign relative trusts to everybody, or wealth to everybody. So if we have n predictors, then the relative trust we assign to everybody, this one's really good at predicting, this one's not so good, is some trust T, that's not the T from the previous slide, that's a new T, some relative, everyone adds up to 1, basically. So you take all the wealth and you add it, and you renormalize. Okay, so now if you have n predictors, and you have each one with a certain trust level, and then each one of them gives you these predictions, I should say predictions, P1 through Pn of how likely they think each person is to win, then you get a new predictor. The whole prediction market, people go look and they say, who's going to win the presidential race? And they look at the prediction market as a whole. And that prediction market is T dot P. It takes our relative trust for everybody, how much they bet, or how much, well, I guess this kind of encodes how much they bet, but if we take how good they are at betting, that would be kind of like creating our own predictor, a new predictor from old. So we take the trust of participant 1 times their prediction plus the trust of participant n times their prediction. So we multiply each prediction by how much we trust its predictor, and that's our prediction for what we think is going to happen. So maybe we have a bunch of different predictors in our head or something, and we construct a new one by thinking about how much we trust each one and adding them all up. So this whole predictor P would be delta plus x, y to the x. X is the set of outcomes, and it outputs a prediction, and it inputs an outcome, like what actually happened. P tensor itself n times would produce n predictions and receive n outcomes. And this polynomial P tensor n internal hom P, what is the position of it? It's a function that takes n predictions and produces 1 prediction. And it takes 1 outcome and produces n outcomes. It takes the outcome and tells each of the n people what their outcome is. So it's a way to combine predictions into 1 and then distribute the outcomes back. A direction of it would be n many predictions and 1 outcome of it. Okay, so the category of maps from P to the n, P tensor n to P in ORF is this coalgebra, this set of coalgebras. And each coalgebra would consist of a set Tn, and for every element of T, a way to take predictions of my n predictors and produce 1 prediction for the whole thing. And be able to take 1 outcome and distribute it to our n predictors. There are many such coalgebras, but the one for us, prediction market, is that we take Tn to be delta n. That's the relative wealth that I talked about on the previous slide, the relative trust levels. And then given any relative trust level for everybody, we use T dot blank to take our n predictions and make 1 prediction. And then we use the thing that takes an outcome and distributes it to everybody. So that's the function from x to the n. Finally, given the predictions and the outcome, We use Bayesian update to get our new trust levels for everybody. So this is kind of how Kelly vetting works, if you've heard of that. You take everyone's prediction, you take the outcome, and you change the relative wealth to accommodate or to reflect the fact that some people got it right and some people got it wrong. So what are dynamic organizational systems? And this is joint work with Brandon Shapiro, those two examples I gave. Artificial neural networks and prediction markets, their monomial categories are operand enriched in org, that's the technical definition. But it's basically a single procedure like gradient descent or Bayesian update that can be performed locally, one per neuron, one per predictor, such that the composites of this procedure again perform the procedure. So gradient descent is the sort of thing that when you connect gradient descenders together, you get another gradient descender. Not all co-algebras would do that, but that one does do it. And that's what a dynamic organizational system is. And the reason I think they might be relevant to consciousness or more like sense-making is that I would love someone in the world to define a dynamic sense-making system. So it's a dynamic organizational system. I have the math that I want to see this in, and maybe it's the wrong math, but it's the closest that I can come so far. I have the math that I would love to see an account of sense-making with it. This dynamic collective sense-maker organizes itself, just like an ANN or a prediction market, through experience, in the sense that it's a single procedure performed locally that works dynamically with the environment, and based on what flows through it, what comes into it and what flows through it, it organizes itself, it adapts to the world, like an artificial neural network during training or a prediction market. And then what I want is that a composite of sense makers, whatever a sense maker is, the composite should again be a sense maker. And so I imagine, based on kind of that first slide, as I said, I was thinking about like understanding your own fit. I imagine that each sense maker is trying to account for the environment, like what's happening to it, and its own fit within it. I imagine the accounting language naturally becoming more systematic through time. So I imagine that there should be some way of saying that we can make a dynamic sense-making system, something that responds and adapts internally based on what flows through it. And the way that it's kind of doing this, instead of doing gradient descent, it's doing something like trying to account for what it's seeing and its own role within it. So to summarize, I want to ask how sense is actually made. How are we making the sense of danger, the sense of humor? How are we able to track the right variables? And I think, at least at my level, at the level of a person in a math class, or a person talking to a friend, we make sense by settling it. A human being makes sense by settling accounts. Everything fits into place. And when that happens, sense gets made, and you can understand the situation better. And then we work to install sense-making systems into the deepest structure as we can. We make policies or whatever, we put it into the bylaws. Now, math is itself a highly systematic and crystallized accounting system. We use it to give very structured and repeatable and regulatable accounts that lets us go to the moon and Mars and make cell phones and satellites. And so this very highly structured, repeatable stuff can be used later to guide our questioning and make our results communicable. And so category theory, being the accounting system for interlocking structures, I think is appropriate for what we're talking about here. Poly itself is a stunningly structured category that's unreasonably effective in computer science. And then finally, dynamic organizational systems, which are based on them, are ways for local entities to self-organize, like artificial neural networks and prediction markets self-organize based on what flows through them. And the open question that I'd love help with is, can we define a dynamic organizational system for sense-making? The math here guides our questioning because it's precise enough that we know what we're saying. And we just have to try to fill in the blanks of what sort of thing could sense-making be. So that's it. Thank you.
Okay, thanks, David. So I think it's hard for me to stand somewhere you can see me. I guess you heard us applause though, right? Yeah, we've still got 5 minutes or 10 minutes for questions. Does anybody have a question? You want to? Yeah. The mic is here.
Oh, so that's the mic. Yeah. Maybe we just use that one. Is that all right? Hi, David. Can you hear me? Oh, that's all. Hi,
David. Can you hear me?
Yes.
Perfect, yeah. I just have another question, so concerning the last slide. So when you use the word self-organize, so could you just point to the math where that self-organization happens as compared to sort of, so for me self-organization is a notion which goes beyond what the part that I understood about dynamic organizational systems. I understand that they're sort of, they rewire themselves, but I perceived it to be still open how they rewire. And I understood that sort of you could then, yeah. So is there something which, is there an interpretation of that self-organization in the math you have, or would that still come on top of it somehow?
I'm really sorry, I'm having trouble hearing and parsing. What I kind of got, so that you can kind of correct me, is that you're looking at this notion of self-organizing and you're saying like, is it really self-organizing or is it just kind of doing a thing? I guess I know your question about self-organizing, but I didn't hear it very well.
Yeah, so I was really just wondering whether there's something in the math which you would interpret as self-organizing. And I'm asking because, so the part of it I understood was really just about, I mean really just, it's a great thing and I really love it, but it was just about sort of rewiring in response to input. Like much like heavy learning wouldn't necessarily be what self-organizing, it's just sort of a way of responding to input.
Yeah, that's great. Yeah, exactly. So sense makers really should self-organize correctly. So why do I allow myself to use this word? What I mean is that this is a framework in which you could make that precise. But when a prediction market changes the relative wealth of everybody based on how well they do, in some sense, I feel like it's doing kind of a good thing, right? It feels fair to kind of call that self-organizing.
Yeah.
Artificial neural networks, like they do get better and better, and they do organize it, like they do change themselves into something that finds features and finds abstractions and stuff like that well enough to compress the internet 1 million times or whatever ChatGPT does. So like it's hard to say when they count as actually self-organizing and when they just count as just some random change that happened. So yeah, defining what self-organizing means might be like, I don't know if that's something we can do.
Yeah.
But you're right to like kind of question like, is this really self-organizing or just changing yourself based on what happens?
But wonderful talk, I really liked it. Thank you very much. Yeah.
Thanks.
Yeah. Yeah. And then.
By the way, it was much clearer when you came up.
Just sit on there.
Can you hear me?
Yes, the camera.
Yeah.
Yeah, the microphone.
Can you hear me?
Yes.
I thank you for the talk, and I also really like the clarity and the message overall. And I know that this may not be your sort of central question or interest, but from the consciousness researcher point of view, I found that this simple feedback into the state and let's say the state part is conscious experience or something like that. This kind of structure can equally apply to this plant path is probably experience or something like that. If I take the expanded maybe over interpret possibly, but this seems to explain equally well for the non-conscious system, like habits or highly overtrained kind of things, and many things like what cerebellum does and things like that. So my question is whether you have any insights into what differentiates the conscious kind of system versus non-conscious system with something similar structure like this.
Yeah, so I guess like people seem more conscious when there's more oxygen, or they are more conscious when there's plants, or they're more conscious. I feel like for me, consciousness, I know I'm probably misusing it, but I want it to mean like the consciousness that's embedded into the cerebellum and the consciousness that's embedded into finding good habits and stuff like that. And I want to call what you're saying experience. And I think you're asking like how do you differentiate experience? But let me just ask, is that even your question?
Yeah.
Is it about experience? Yeah, I don't know what experience is. I don't know how you would find it. It might just be this coherence of different senses, like the fact that but I can't say. I mean, if that was true, then I would think organizations would have experience, and I don't think that they do. I mean, I don't know that they do. So I don't know what experience is.
Okay.
Yeah.
That's fine. Yeah.
Yeah, we have another question coming up. Yeah, I think if you stand there.
Hi, David, can you hear me?
Yes.
First of all, I found it a really beautiful talk and a very beautiful framework that you developed to kind of phrase all of those questions about the organization of systems and subsystems and so on. But at the end of the day, you kind of pose what you want as a question to us, so to say. What could it actually be that is that principle where the student, for instance, does some work and then by doing that work makes sense? So there must be some sort of optimization principle that ideally could be phrased within the language that you developed, but what that optimization principle is something that you left open or asked as a question, so to say. And my question would be, surely you already thought about it and have maybe at least some ideas about it, and I would be curious about those. So what do you think is actually an optimization principle that one, or do you have any ideas about the optimization principle where things fall into place and suddenly become coherent, or one could phrase that?
I would love to know. So I think it might have something to do with accounting. When I think of, I just love math, and for me it's like an accounting system. And and then I think we make accounts of things. We use math for very systematic accounting. But that student who is sitting there like, no, wait, but you said this and that, they can't account for all the things on the board. They're not able to formulate that in some kind of like, the accounts aren't fitting together. And so I think there's something like that. And I think there's something like, and this feels like a totally different way of looking at it, there's something like distributing the load. Like if you have like a sheet or something and you drop a ball onto it, like it kind of like distributes the load. And I think society is trying to distribute the load of like trying to, whatever we're trying to do, maybe it's kind of entropy maximization or whatever, but like we're trying to distribute the load of this difficult problem we have of being a world. Like what thing needs to get handled by the world, and then we're trying to distribute this load. So you're asking me, hey, can you help me handle a little bit of this load right now? Like I like what you're saying, but I'm missing this piece. And I say like, well, I don't know if I can help you, but here's something that I've thought about, and we kind of distribute the difficulty through ourselves, and that's what all this communication and sense making allows, so that one person isn't like, overused, overworked, and it fails. By sense making, we can see like when a person or a cell or whatever is being overworked and take some of the load off of them, and that's kind of what this is all about, or something.
Thank you very much.
Yeah, thanks.
Yeah, sure, one more. Maybe quick.
Hi, David. Thank you for the very lovely talk. And I share the view of mathematics as an accounting system, but also the important point is accounting, or the make sense, is the cause of such make sense is some kind of frustrating or something, the contradiction or something. Do you have any ideas to how to say account, or what is the frustration, or what makes frustration in the category theoretic?
That's a good question. I don't know. When things don't make sense, it's frustrating, for sure. I guess from this kind of Bristolian point of view, it doesn't make sense. It also doesn't make sense when I'm not enough for what I need, for where I am to be. Like, it's frustrating when I'm not enough. Why am I locked in traffic? Why can I not get where I need to go? It doesn't make sense. It's very frustrating. But yeah, I don't know. I don't know why we're willing to be frustrated. Why we don't just collapse. But what keeps us frustrated?
Yeah, but I think the cohomology or something is maybe to measure such frustrating or ambiguity or something, and yeah, such a just for the ideas. Okay.
That's interesting. Cool. Thank you.
Yeah. Let's talk again in some future.
Okay, sounds good.
Okay, yeah, let's thank David again.